Hello, everyone. I'm Jet Aguilar from the Astronomical League of the Philippines, and I will be hosting today's webinar. Thank you so much for joining us for our 2024 Astronomy Expert Speaker Series online lectures, which will also be part of our ALP National Astronomy Week 2024 opening program. I'm very happy to welcome all our attendees, not only from the Philippines, but also from the other parts of the world. Thank you so much for attending, and I hope you will enjoy today's webinar. For today, we have a very interesting topic to be discussed by none other than Dr. Jonathan McDowell, an astrophysicist with the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, and a member of the Chandra X-ray Center, which operates the Chandra X-ray Observatory spacecraft. Dr. McDowell will be talking about how Chandra and other X-ray telescopes are making new discoveries in the invisible universe. My fellow ALP member, Ms. Imelda Joson, will be doing the introduction for our esteemed speaker later. For those who are not able to register but would still want to watch this ongoing webinar, we are currently live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum, where you can watch this now live. And before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for all. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We'll be doing our best to read and answer all your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. So enjoy and let us all have fun learning. Here is the program flow for the webinar. And before we continue with the main program, I mentioned that this is also part of our opening program for National Astronomy Week. And I would like to give you a brief historical background of why we celebrate National Astronomy Week in the Philippines. This third week of February in the Philippines, we are celebrating National Astronomy Week based on Presidential Proclamation number 130 of President Fidel Ramos issued on February 27, 1993. This presidential proclamation declares the third week of February of every year as National Astronomy Week. The proclamation recognizes the universal appeal of astronomy and its significance in various fields of human interest and endeavor. The purpose of declaring National Astronomy Week is to promote the study of astronomy, raise awareness about its importance in advancing science, and encourage active participation in environmental conservation. Having said that, do you know that the first ever National Astronomy Week in the Philippines was actually celebrated in April 16 to 22 in 1990, or 3 years before the presidential proclamation? This was due to Proclamation number 544, signed by then-President Corazon Aquino on March 26 of that year, declaring April 16 to 22 as National Astronomy Week. This idea of National Astronomy Week was first proposed by our own Ms. Imelda Joson and Mr. Edwin Aguirre of the Philippine Astronomical Society. The second National Astronomy Week was celebrated in February 16 to 22, 1992, with Presidential Proclamation number 863, signed also by President Corazon Aquino in February 14, 1992. On February 16, 1992, the second NAW celebration was opened at the National Museum Planetarium at Rizal Park, with Vice President Salvador Doy Laruel as the guest of honor and speaker. In her proclamation, President Aquino said that while astronomy serves as our window to the beauty and wonders of the universe, it also enables us to appreciate the uniqueness and fragility of our home planet Earth. On that beautiful note, let me call now on Ms. Imelda Joson, one of the founders of National Astronomy Week, to introduce our esteemed speaker.
Thank you so much, Jet. And I would like to thank everybody who kept the National Astronomy Week celebration going for the past 34 years now. And June, I'd like to thank you also for following up with the presidential proclamation from President Ramos. And I'd like to thank our dear friend, longtime friend, Jonathan, whom we haven't seen for almost 18 years now. But, you know, when I called him to be a part of this celebration, he never ignored my request, even though we haven't seen each other for a long time. So, Dr. Jonathan McDowell is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. A staff member of the Chandra X-ray Center, he studies black holes, quasars, and X-ray sources in galaxies, as well as developing data analysis software for the X-ray astronomy community. Jonathan earned his BA in mathematics in 1981 and a PhD in astrophysics in 1986 from the University of Cambridge in England. He previously worked at the Royal Greenwich Observatory, the Jodrell Bank Radio Observatory, and NASA's Marshall Space Flight Center. Jonathan's scientific publications include studies of the cosmological extragalactic background light and the possibility that massive black holes contribute to the dark matter problem. The X-ray emission from the merging galaxy ARP 220, the nature of the broad emission line region in quasars, and the broadband spectral energy distributions of quasars. He helped design the CIAO data analysis package and the software infrastructure for the Chandra X-ray Observatory data processing pipeline. Jonathan is also the editor of Jonathan's Space Report, a free internet newsletter founded in 1989, which provides technical details of satellite launches and is a contributing editor to Sky and Telescope magazine. Jonathan's website provides the most comprehensive historical list of satellite launch information, starting with Sputnik, and he carries out research on space history topics using original sources, including declassified Department of Defense documents and Russian language publications. Jonathan is a fellow of the Royal Astronomical Society and the American Astronomical Society. He won the Sir Arthur Clarke Award for Individual Space Achievement in 2019. He was awarded the Prix Alexandre Antonov of the French Astronomical Society in 2020 for contributions to astronautics, culture, and popularization, and the Geoffrey Padreau Space Award of the Royal Aeronautical Society for service to the space industry. In 1993, the International Astronomical Union named asteroid 1933 as 4589 McDowell in his honor. Ladies and gentlemen, let us welcome Dr. Jonathan McDowell.
Thank you very much, and it's nice to see my old friends there on the screen. We've known each other for a very long time, and it's an honor to be invited to address the Astronomical League of the Philippines. I'm very excited to do this. And what I want to talk to you about today is the work that my colleagues and I have done with a spacecraft called the Chandra X-ray Observatory. And if you want to, yeah, there we go. And maybe put it in presentation mode. Perfect. And so I'm going to talk about the Chandra X-ray Observatory and the invisible universe that it reveals. And so I'm going to start by going all the way back to the 1500s. This is a woodcut drawing by Tycho Brahe of a part of the sky where he saw a new star appear in Cassiopeia, and it was visible to the naked eye, and then it slowly faded from view. And if you look at that part of the sky now with an ordinary telescope, even one as awesome as Hubble, next slide, you see I mean, no part of the sky is boring, let's be honest. For astronomers, no part of the sky is boring. But if you go back to that optical one, thank you, yeah. There's really nothing much going on there in the optical. But if you then look at the same part of the sky with an X-ray telescope, then you see, thank you, this enormous object that, oh, go back to the, let's stick on that for a minute. This is a supernova remnant. It's an exploding ball of gas many light years across. And the reason that you can only see it in X-rays is that when gas is at 1,000,000 degrees, it is transparent to ordinary light. And so you're zooming along that part of space. If you only have ordinary eyes, you don't see this at all. You run into this 1,000,000-degree ball of gas. And it's expanding. We can see it expand over a period of years. And it glows like crazy in X-rays. When matter is at 1,000,000 degrees, it shines in X-rays. So what are X-rays? Let's just recap a little bit on that. Next slide, please. And so people are sometimes a bit confused when I talk about X-ray astronomy, and they think it's like X-raying the sky like when you X-ray a broken arm. And what I think confuses people is that X-ray of the hand that you see there, the X-rays are actually the white bit, and the hand is photobombing the X-ray lamp and casting a shadow. And so when I talk about X-raying, X-ray observations of space, I'm not talking about that shadow. I'm talking about the equivalent of the X-ray lamp that shines through your bones and to the X-ray camera. And so if X-rays are just a color of light that our eyes can't see. So next slide. And so the way I think of it is that if you think of visible light photons as like raindrops, and so you have a bunch of raindrops, and each one is very small, and you can have an awful lot of rain. I grew up in England. I know there's a lot of rain, but it's still not going to hurt you, because even though there are many, many, many raindrops, each one doesn't have a lot of energy. But if you get in a hailstorm where each object in the hailstorm is big and chunky, it can really do some damage. And that's what X-rays are. They're a color of light where each packet of energy, each photon has a lot of energy, packs a big wallop, and can do some damage. And so that's why you'll never get a suntan from just shining lots of ordinary room lights on you, but you can get a tan or worse by shining a little bit of X-ray light on you. And so what's really happening is that there are two things going on in light. There's the intensity, which is the number of photons coming through to you. And there's the energy of each photon, which is encoded in our brains as color. Blue light are photons with a lot of energy. Red light are photons with a little bit of energy. And we record that in our eyes, turn that in our optic nerve in our brains to the concepts of red and blue. And so X-rays, if we go on to the next slide, are just on this rainbow, and you see the visible rainbow in the middle where you have red through violet is only a tiny fraction of the full electromagnetic spectrum, where we see all the way from, on either side, a lower energy light than red is infrared light. You've heard of infrared. And then below that, you have radio waves. Higher energy light than blue and violet light is ultraviolet. That's the stuff that gives you a tan. And then even beyond ultraviolet, we go to X-rays and gamma rays. And so that's where X-rays fit on the spectrum. They're just very, very, very blue light. And each of these different kinds of light is made by different things in space. And we use different telescopes to see them. And so our telescope Chandra is specialized to detect X-rays in space. Next slide. And X-rays are made by a bunch of different kinds of object in space, but they all have in common that they're seriously messed up. They're where things get violent in the universe. And so the main sources are shock waves. And on the left, we see a picture of the expanding ring of the shock wave from an exploding star in Large Magellanic Cloud, supernova 1987A. Another way you can get X-rays is if you have elementary particles spinning really fast in a magnetic field, like a natural particle accelerator, like the Large Hadron Collider in Geneva or something like that, but a natural phenomenon. And in the middle there, we have the Crab Nebula, which has a spinning pulsar with a strong magnetic field, and that creates X-rays from the synchrotron radiation of the magnetic field. And then the third way is slightly different. When you squeeze matter, it gets hot. Increase the pressure and you make things warmer. And gravity likes to squeeze matter. And so we can release energy from gas in space when you have a lot of gravity around. And a good example is a cluster of galaxies. A cluster of galaxies, like the one pictured on the right, has a mass of maybe 1,000 billion suns. And that's enough to squeeze the gas that's orbiting near the cluster to make it as hot as 10 or 20 million degrees. And so you get X-rays from that. And so, when you look at the sky at night with our boring, ordinary optical eyes, what you see is energy from nuclear fusion. Stars shine from nuclear fusion. And so starlight is fusion light. But when you look at the sky in X-rays, next slide, what you're seeing there, this is a picture of the sky taken by the German Rosat satellite in 1990. And there's 100,000 X-ray stars, quote unquote, in this picture. But each one of them is not actually a star, and it's not shining by nuclear fusion. What you're seeing here, almost all of these sources are quasars. They're supermassive black holes where the matter is falling into the black hole. And, famously, right, when matter falls into a black hole, you can't see it anymore. The black hole is black. But here's the trick. On the way in, the gravity of the black hole squeezes the matter, makes it really hot, and the matter glows. And so just before it disappears into the black hole, it gets really bright, and that gives away where the black hole is. And so that's what we're seeing. We're seeing X-rays not from nuclear fusion, but from gravity accretion is the word. The black holes are accreting matter. They're gaining matter that's just nearby, and they're sucking it in. And I think of these quasars then as gravity reactors by analogy to the fusion reactors that we call stars. And so it's a whole other different source of energy in the universe that we didn't appreciate was a really important part of the energy balance of the universe until we got X-ray space telescopes. Next slide, please. So now we get on to our wonderful toy, the Chandra X-ray Observatory, which is a 5-ton spacecraft in orbit around the Earth. And this year is its 25th birthday. We're definitely going to have a cake. And it was launched on the space shuttle, and it's been orbiting the Earth for 25 years. And it really revolutionized X-ray astronomy because for the first time, it's a telescope that can take really sharp pictures in the X-ray. So if we go to the next slide. So The thing about X-rays is they come across the universe. In the case of the objects I look at, they've traveled across the universe for 1 billion years. And yet, they don't get to the surface of the Earth. They get stopped in the last second of that billion-year journey by the Earth's atmosphere, which is super annoying for X-ray astronomers, although actually really good news for the rest of us because we don't want to be irradiated by X-rays all the time. And so in order to see the X-rays, you just need to put your telescope a little bit above the atmosphere, right? It's not that you're getting closer to the things that you're looking at, but you're getting out of the murk of the atmosphere. And I think of it a bit like, you know, when you're in a swimming pool and you're swimming underwater, you can't see very far. And then when you put your head up above the water, suddenly you can see a lot more clearly. And that's what we're doing. We're taking our X-ray telescope and we're putting it above the Earth's atmosphere. And the plot that we see at the bottom here shows on the left the Earth, on the right the moon, and then this ellipse, this white ellipse on the left is the orbit of the Chandra spacecraft. And so you see it goes about 1/4 of the way to the moon. And the pink bands surrounding the Earth are the famous Van Allen belts, the magnetosphere, that have a lot of radiation. And we can't observe while we're in the Van Allen belts. So we can only observe the part of that ellipse when we're outside the pink part. And so our 2-day orbit around the Earth, every 2.5 days, we go around this ellipse. And at the far point of the ellipse, we can observe. And then at the point that's close to the Earth, we have to shut down for a bit. But it actually goes, because of Kepler's laws, it goes much slower at the high point. And so we actually get a good 2 days worth of observing on that orbit. And so Chandra's been going around and around in that ellipse for 25 years now, taking really good, sharp images of the X-ray sky. Next slide. And how do you make pictures in X-rays? Some of you, I know, are amateur astronomers, have probably made telescopes of your own. And, you know, you've maybe ground a parabola into glass. I had friends who did that when I was in college. I did not have the patience to do mirror grinding. But you know, you make a nice reflective parabola. But that's not going to work with X-rays. The X-rays are going to come in and either be absorbed by the mirror or they're going to go straight through it. You can't just bounce it off a reflective mirror. What you can do, though, is something called grazing incidence, which is that you skip it off at a very slight angle to the mirror. So you put the mirror sideways on to where the light is coming, and it comes in at a 1 degree angle to the mirror and then deviates by another degree. It just makes a very slight course change. And so if you put a couple of these, so if you make a mirror that's almost like a cylinder, you can reflect the light off the inside of the cylinder and bring it to a focus. And that's actually kind of cool because although it's very inefficient because sine of 1 degree, you have to have a lot of reflective surface to have a little collecting area, but still you don't use the whole middle of the cylinder where the light isn't hitting the mirrors. And so you can put another mirror slightly smaller inside that one. And Chandra actually has 4 mirrors nested one inside the other, as you can see on this picture. And they all contribute to collecting the light and bringing it to exactly the same focus, or very nearly almost exactly the same focus, because we slightly screwed up the 4th one when we were building it. But so these X-ray mirrors then are very different from ordinary mirrors. They use this grazing incidence, but also you can't make them out of regular glass or aluminize them. You know, if you aluminize them, you know, these little aluminum atoms, they're pathetic. They're low mass. And the X-ray has so much energy that instead of reflecting off the aluminum atom, it's going to move the atom. And so you have to have much heavier atoms to reflect off. And you either gold or iridium, and we coat our mirrors with iridium. So that's already quite expensive. You have these heavy mirrors coated with iridium, and they have to be polished really, really well because the wavelength of X-ray light is 1,000 times smaller than the wavelength of visible light. And so when you're with your grinding stone, grinding your X-ray mirror, right, you've got to kind of spot a little atom sticking up and grind it back down. It's got to be smooth at the atomic scale, right? Wavelength is about an angstrom, and that's about the size of an atom. So they have to be incredibly smooth. So you're starting to get now that this is quite an expensive mirror to make. And now you've got to put it on a rocket and shoot it above the atmosphere. So it's an ambitious project. Next slide. So that's how the X-ray telescope works. We put it inside a spacecraft that is 10 meters long. And the spacecraft has the mirrors if we look at the picture on the left, the mirrors are at the right-hand side, the cameras are at the left-hand side, and there's a big long empty tube connecting the two that's about 10 meters long. That's the focal length of the spacecraft. And then around the mirrors, we wrap the electronics of the spacecraft and the solar panels that give it electricity. And that's really all there is to it. You have this machine that can orient itself using gyroscopes, using reaction wheels. You boost it up to this high orbit, you open the lens cap, and you start focusing X-rays onto the cameras at the far end. The cameras themselves are a miracle, and as much as the mirrors are incredible because they focus the X-rays in this 10-meter long machine to a spot that is only 25 microns across. So all of this 5-ton huge spacecraft is to kind of persuade the X-rays to collect in this one tiny spot. And so next slide. And this is a picture of the camera, our main camera, which is called AESS, the Advanced CCD Imaging Spectrometer. And if you look at this camera, you see in the middle, there's sort of a T-shaped area with 6 little squares in a row, and then another 4 little squares below that in a square array. And each of those is a 1 megapixel chip. And it's a chip that's not terribly different from the chips in your phones that you use to take pictures, except that they're optimized, instead of to take visible pictures, of course, they take X-ray pictures. And so they take X-ray color pictures. And so the total assembly is a 10 megapixel camera, which is not very impressive these days, but it was pretty darn impressive for 1999, even in an optical camera, never mind an X-ray one. And so that lets us, and so each of these pixels, right, has each of these chips has 1,000 pixels across, and in one pixel, we can put the X-ray image of a star in these tiny little area in the camera. And we have to keep this camera cool. We keep it at about minus 120 degrees Celsius. Which we do just by passive cooling because it's out in space there. But we have to be very careful we don't heat it with the sun too much. Next slide. And then we also have what are called transmission gratings. I'm not going to talk about these too much, but see these enormous things that are about the size of a person have lots and lots of little gold-coated facets on them that when the X-rays pass through them, they're dispersed into a rainbow, into a spectrum. And so that can give you a high-resolution spectrum in the X-ray. We don't want that all the time, so these things actually swing through 90 degrees in and out of the optical path of the telescope. Sometimes they're in the way of Chandra's view of the sky, and sometimes they aren't. But when they're in the way, then they give us these very high resolution spectra. All right, next slide, please. And so Chandra on the top left there is sitting out in space in orbiting the Earth. Whoops, back a bit. Let's see if we can get back to that previous slide to this one. There we go. And so it's out there, you know, we're sitting at the Science Center on the campus of Harvard University in Cambridge, Massachusetts. And we talk to our Mission Control Center, which is in Burlington, Mass. Edwin and Imelda, I think when you were here, it was still in Kendall Square, but they booted us out to the burbs. We then send commands to the Jet Propulsion Laboratory in Pasadena, California. Many of you may know that as the headquarters for the Mars rovers and the Voyagers and so on. And they send it to the 3 Deep Space Network dishes in California, Spain, and Australia. So as the Earth turns, one of these dishes can see Chandra, wherever it is in space. And so these crucial sites, these 3 sites on the world, are sort of, I think of them as Earth's USB ports. They're the place where the Earth talks to deep space, and all of the data from all of the American probes, the Voyagers, the Mars probes, and then Pluto probe and everything, come to one of these 3 spots. And so we have to share these dishes with the other much less important missions like Mars probes. Boring. No, you want to do X-ray astronomy, right? So we get about 1 hour out of every 8 hours on the dishes to talk to Chandra, tell it what to look at next, and to download the data back to Harvard to distribute to the astronomical community. Next slide. And so we launched it on the Space Shuttle in 1999. And at the bottom there, you see the Space Shuttle Columbia on the pad about to launch and launching. And embarrassing at the top, you see a much younger version of me. We already saw a younger version of Imelda and Edwin, so I had to put one in for me. There I am standing by the launch pad just before the launch. The Space Shuttle went into a low orbit around the Earth. And now next slide. And you can see in this picture, the shiny, crinkly silver thing that looks like aluminum foil is the thermal insulation wrapping the Chandra X-ray Observatory as it sits in the payload bay of the Space Shuttle Columbia orbiting the Earth. And so they've pushed it out on springs. And next slide, please. And here is a picture taken by one of the astronauts showing Chandra sailing away. And right at the bottom, you can see a sort of gold, copper colored thing that is the enormous 20-ton firework that would fire 45 minutes later to boost Chandra into its much higher orbit that the space shuttle itself couldn't get to. We wanted to be above the radiation belts, so we needed this big rocket to push it even further up. And so that was the last view the astronauts had of Chandra before it went up to the high orbit. Meanwhile, next slide, in Guyane Française in South America, the Europeans were preparing this rocket for launch, which next slide put up Chandra's European cousin, the XMM Newton Observatory. And so it's also been operating for 25 years. And we think of them not as rivals, but as complementary. If you look at the next slide, here's pictures of a galaxy taken on the left with Chandra and on the right with the European spacecraft. Chandra's pictures are much sharper, and that means we can see fainter X-ray sources that XMM can't see. XMM's mirrors aren't as expensive, aren't as exquisite, but it has more of them. It has more collecting area. So it can get more data on the brighter sources. It just can't see the fainter sources. And so that makes them really nice and complementary for different scientific questions. But I'm going to carry on talking mostly about Chandra. I just wanted to remind you, it's not the only X-ray telescope that we have. So let's look a bit more at the science of what we do with Chandra. Next slide. So this is actually an infrared picture of a star cluster that is 10,000 light years away, NGC 281. And you can see a bunch of stars, and you can see a lot of glowing gas. And why is the gas glowing? It's glowing because it's being irradiated with ionizing radiation. Next slide. And when we look at the same part of the sky with Chandra, we see the X-rays from the young stars that are causing that gas to glow. And so by combining Chandra data with data from ordinary telescopes, we can get a much more complete picture of what's going on. Next slide, in this star cluster. And there's the combined picture showing Chandra in purple, and the other colors are the optical, the infrared. And so you can see this X-ray sources right in the middle of this area of hot gas. And this is going to be a sort of recurring theme here of combining the data. Next slide. This is another exploding star. This is the supernova remnant Cassiopeia A. Unlike the first one I showed you at the beginning of the talk, you can actually see something here in the visible. You can see something's going on here. Few wisps of gas left. It's not super spectacular, but it's there. When you look at the same part of the sky in X-rays, this time with an older X-ray telescope called ROSAT, next slide. This is a picture from ROSAT. It's one of the brightest X-ray sources in the sky, Cas A. It's a couple arc minutes across. And you just see a sort of glowing, vague, blobby thing. So you spend an extra $1 billion and get yourself a nicer X-ray telescope. And this is about a 1-day exposure with ROSAT. If you look at a 1-hour exposure with Chandra, next slide. Here is 1 hour with Chandra at the same object, and you can see so much more detail. You can even see a little dot in the middle of this exploding star that is the remnant of the star. It's the neutron star left over from the explosion. And so Chandra's sharp image is crucial to understanding what's going on in this exploding star. And if you look at it not for an hour with Chandra, but for 11 straight days staring at it with Chandra, next slide, you get this picture, an X-ray color picture. So the different colors represent different energies. And in this particular picture, we've split it up by spectral emission lines, the characteristic radiation of different chemical elements. And so the blue color, the blue-purple color, is from iron, and the red color is from silicon. And then the green is the rest of the light, that is the shock wave from the expanding supernova shock. And so, as you know, we're all made of stardust. The elements in our bodies were made in explosions like this. Nuclear reaction rates in stars explain why iron is common. This makes a lot of it. You know, platinum and gold are really rare. You don't get as much made in these explosions. And so we can study the freshly made elements, freshly baked, just out of the oven, from this exploding star, with the X-rays coming from them. They haven't cooled down yet. And we can study, and we can compare this to the theoretical models of supernovae, which have, if any of you have studied this kind of thing, you'll know that the textbooks have these nice circular diagrams where there's a shell of one element and a shell of another element, and it all looks very pretty and simple. And then when you look at this data, you immediately see, well, not so much. It's kind of irregular, and it looks like there's a jet of silicon coming out of one side, maybe the North Pole of the star or something like that. And so there's a lot of physics that's encoded in this image, which, by the way, this object is 11,000 light years away, and the picture you're seeing is 16 light years from one side to the other. So this is not a small explosion. This is a very large object. Next slide. So this is an optical light picture of the direction to the center of our galaxy. The center of our galaxy is 30,000 light years away. So we're seeing it as it was in sort of caveman times. And you see the combined light of billions of stars. And you also see the annoying dust lane right across the middle. It's basically cosmic soot that prevents us from seeing the center of the galaxy at all. And when you zoom into that, next slide, this is the direction toward the very center of the galaxy as seen in optical. But what you're seeing here is not the center of the galaxy. You're seeing nearby stars that are in between us and the center of the galaxy. And you can't see the center of the galaxy because it's so hazy. All of this dirt in between us and it means that in optical light, you can never see that galactic center. But if you switch an X-ray telescope in, next slide, now you see there's all kinds of stuff going on. So this is exactly the same part of the sky as I just showed you, but in X-rays instead of visible light. And so that really brings home how much you can see with an X-ray telescope that you can't see even with the most exquisite Hubble image. And so what you're seeing here is hot gas in red, and in blue, emission from binary stars and other active stars and exploding stars. And then right in the middle where the arrow points is light from matter falling into the central black hole, Sagittarius A star, in the center of the galaxy. And so Chandra provides us with an unparalleled way to probe the exotic physics that's happening in the middle of the galaxy. Next slide. But that's only 30,000 light years. That's boring local stuff. Let's actually go for a ride now. And we're going 12 million light years away to the nearby galaxy Cen-A, Centaurus A, otherwise known as NGC 5128. Already in the visible light image, it looks a bit odd because it's an elliptical galaxy. It's kind of roundish. It doesn't have the beautiful spiral arms, but it does have a weird dust lane across it. So it was always a bit puzzling. But when you look at it in X-rays, next slide. Actually, I think what I'm showing in the next slide is the combination. See if we can get to that next slide. Yeah, here we go. Yeah, this is the combined light, the same object combining the visible radio in pink and X-ray in blue. And what you see, completely you didn't see it in the visible light image, you see that there's a pair of jets coming out, one to the top left and the other to the bottom right, plowing their way through intergalactic space, about 30,000 light years from one end to the other. And when we study it in detail in the X-ray, we see that it's all coming, these jets are coming out from the very, very middle of the galaxy, of this galaxy Cen-A, from the central 1 light year. So 30,000 light years across, but all coming from the central 1 light year. And it turns out these jets are matter traveling at 99% of the speed of light. And they're being squirted out from the region close to the black hole. So it turns out that the black hole is a messy eater. 90% of the stuff you feed to it goes down the black hole, but maybe 10% gets caught in the magnetic field before it falls into the black hole and gets shot out in these jets, which are incredibly powerful and punch their way out of the galaxy that they're sitting in. Next slide. Here's another galaxy. This one's 10 times further away. It's 130 million light years away. NGC 4993, very delicate spiral galaxy. But one day, the LIGO experiment, yeah, we can go to that next slide. The LIGO experiment that detects gravitational waves detected a ripple in space-time coming from this part of the sky. So if we can get to that next slide showing the merging neutron stars. Here we go. This is an artist's illustration of these two blue things are meant to be neutron stars that are orbiting each other. And as they orbit, the gravitational waves leak away energy from the orbit, and they spin closer and closer and faster and faster and closer and closer and faster and faster. And then boom, they merge. And we looked at, immediately swung Chandra to look at this as soon as the LIGO folks told us they'd seen something. And what we saw in the bottom two panels on the left, only 9 days after the merger, we saw an X-ray glow from that part of the sky. And then a few months later, we saw a much brighter X-ray glow when we went back. And so this is the expanding ejecta that's becoming a supernova remnant from the merged neutron stars. And so with Chandra, we can get a very precise position in that galaxy for where the merger happened, because LIGO, you know, it's great at detecting these things, but it's kind of like, well, it's sort of over there somewhere. They don't really know exactly where it comes from. And so sort of like me when I take my glasses off. So Chandra can give you a really nice, accurate position with this technique. If we go to the next slide, a slight digression. This is not from Chandra, but what we see in the bottom panel is the famous gravitational wave chirp, this line that's going from bottom left and then it curves upwards. There is this gravitational wave signal as the stars are getting closer and closer and faster and faster, and it's like as the two things merge. And then in the upper panels, we see the gamma ray signals from the Fermi and Integral spacecraft. And we see that 2 seconds after the merger, whoom, there's a flash in gamma rays. And for me, this is really profound. Because remember, this galaxy is 130 million light years away, which means that these signals have been crossing space for 130 million years. And the light signal, the gamma ray light, the electromagnetic signal, arrives at Earth within a couple of seconds of the gravity signal. And that couple of second delay is we think it's due to how initially the explosion is opaque and the light doesn't get out for a bit. And so that's about what we expect. And so we think that they're seeing exactly the same event. But what that means is over 130 to within 2 seconds, over 130 million years, the light and the gravity traveled at exactly the same speed, which is what physics said should happen. Because the speed of light isn't just the speed of light, it's the speed of everything that doesn't have mass, and that includes gravity. And so this is beautiful proof that the speed of gravity and the speed of light are the same. So next slide. And so I'm going to go even further out into the universe now in my last few slides and talk about clusters of galaxies. And so this picture, almost all the blobs you see in this picture are not stars. They're entire galaxies made of hundreds of billions of stars. And if you look closely, you can see there's kind of a grouping of them at center left and another grouping a little above the midpoint in the right. And there are two clusters of galaxies, and we now know that the cluster on the right has passed through the cluster on the left. This is an enormous cosmic train wreck. And when we look in X-rays, next slide, we see the hot gas in the clusters of galaxies. And we see on the right, there's this shock wave from the gas in cluster number 2 plowing its way through the gas in cluster number 1. So that's great. And we measure the amount of matter there, and we say that there's actually this invisible X-ray gas is 10 times as much matter as the matter in the stars in the visible galaxies. So when you look at a cluster of galaxies, you're really looking at the raisins in a much bigger pudding, an invisible million-degree hot pudding of gas. And so really Chandra will let you see where most of the mass is most of the ordinary mass is, the mass made of elements that we understand, in a cluster of galaxies. But there's another trick that we can play. And the other trick that we can play is we can look at even more distant galaxies behind the cluster galaxies. And the images of those more distant galaxies are distorted by the gravity of the clusters and make the make those images distorted. We can measure that. It's a phenomenon called weak lensing. It's a general relativity phenomenon. So if we go to the next slide, this is just combining the X-ray and visible light. And then if we go to the next slide, at the bottom left, the blue at the bottom left is the where we see the signal of the weak lensing, the gravitational lensing being done by the bulk of the matter. And the super weird thing in this object is that the blue is not in the same position as the pink, which is the hot X-ray gas. So most of the regular matter is in the pink clouds, but the total mass is in the blue blobs. Why is it not in the same place? Because the blue blobs are mostly the famous dark matter. And what's happened is, as cluster number 2 smashes through cluster number 1 at supersonic speed, the gas feels the gravity of the other cluster that's slowing it down, but it also feels the shock wave of the gas hitting the other gas and showing it down. But the dark matter only feels the gravity. It doesn't feel the shock wave because dark matter doesn't interact electromagnetically. And so shock waves don't bother it. They go right through it. And so the dark matter keeps on going. It slows down a bit, but it doesn't slow down as much as the gas. And so this is a natural physics experiment. By slamming 2 large masses together, you can separate out the dark matter and the ordinary matter. You need whole clusters of galaxies to do it and smash them together at supersonic speeds. But when you do that, when nature does it for you, you can see this really proves that there is such a thing as dark matter. Because this is not just, oh, the gravity law has changed a bit, because we've managed actually to take the dark matter and distill it out from the regular matter. It's in a different place. And so this is a really profound discovery that was only possible by combining Chandra data with visible light data. So if we go on to the next slide, I just want to finish off with a couple of recent discoveries that we've made. The top right, we see a bunch of little dots that are quasars that weren't visible in the, can't be seen with visible telescopes because they're hidden inside dust clouds. I'll skip those other 2 and let's go on to the next slide. One of the very latest discoveries. So on the left here, we have another cluster of galaxies, but behind it is a much more distant quasar. And we zoom in on the right panel, well, you see the little blobby pixels there are a quasar at redshift 10, which is 32 billion light years away from us. Another way of thinking about it is we're seeing it as it was only 500 million years after the Big Bang. And Chandra's measurements show that there's a black hole in there that's at least 10 million times the mass of our sun, which is very early in the universe to be making such a big black hole. And it's hiding behind this foreground cluster that's a mere 4 billion light years away. But by combining Chandra data on the top panels with James Webb data on the bottom left, we get this picture on the bottom right that has the combined data. We can probe both the nearby cluster and the quasar hiding behind it and magnified by it. And so we're really now still making new discoveries with Chandra 25 years after its launch, probing even further into the universe with Chandra than we've done before, 32 billion light years, and doing it in conjunction with the new capabilities like James Webb that let us squeeze the best physics out of our inquiries. So what I want to mention is that when you observe with Chandra, well, first, anyone can propose to observe with Chandra. The deadline for this year is mid-March, and you do need some expertise, right? But astronomers all over the world are going to be competing with their proposals to use Chandra for the next year. If you win a Chandra proposal, you get the data for a year, and then it goes public. And so we have this huge archive of public data. Next slide. And we've published a catalog of over 300,000 X-ray sources all across the sky, seen with Chandra. So that's all public data. You can download it at cxc.harvard.edu. The software is also public and open source. It runs on Mac and Linux. So I'm afraid it doesn't run on Windows. So we try and get this data that we've accumulated out to the public so that you can use it. There's a public website at chandra.harvard.edu that has all the pretty pictures if you just want to see those. And next slide, if there is one. Yeah, so I'm just going to wrap up by saying these spacecraft were meant for 5-year missions. They're now almost 25 years old. Chandra, you know, it's like me, it's showing its age. It's lost some sensitivity in these cameras in certain X-ray colors, but in other colors, it's still seeing as sharp as when it was young. Its thermal insulation isn't working well anymore, so we have to plan observations carefully because, like, oh, its rear end's getting too hot, its nose is getting too cold. We better move it around and look at something else. But both Chandra and XMM plan to keep operating for years to come. Europe's funded a successor to XMM called Athena. We were planning a project called Lynx, but it didn't get approved. So right now, there is no funded follow-on to Chandra. It's still the best X-ray telescope in the solar system. We're going to keep nursing it along in its old age and getting great science out of it for as long as we possibly can. And with that, I'll wrap up and take questions. And yeah, that's a good slide to leave up. So I see that there are a couple questions in the Q&A. Dante, can I go straight to those, Jose, or do you want to?
Yeah, I can read it for you. First, there's a question here in the chat box. Wait. In the X-ray image of Cassiopeia A, why does it seem that the iron or blue components are irregularly distributed?
Right. Why are the different elements irregularly distributed? Is that the question in Cas A?
Yeah.
Yeah. Well, that's the question, right? What we think is the star, when it blew up, was spinning. And so some of the material went out along the poles, right? And so it's extended in that sense, but different layers were spinning at different rates, and so they all ended up slightly different directions. So yeah, it's much more complicated than we had expected.
Okay.
I see there's a question in the Q&A.
Yeah.
Why
I'll
was
read the
telescope...
question. Yeah. Why is the telescope called Chandra? Yeah.
Yeah. Why is the telescope called Chandra? It's named in honor of the guy who really came up with the idea of black holes in their modern form, Subrahmanyan Chandrasekhar, who is an Indian-born astronomer, who then did his studies in England with Eddington, and then moved to the United States and spent many years in the United States he got the Nobel Prize eventually. He got all kinds of discoveries, including a lot of the early theoretical work on black holes. And he was known as Chandra to all his friends. That's why it was named after him. And actually, we had Mrs. Chandra at the launch as a guest to celebrate. So that was nice.
And the next question. Yeah.
Before you go any further, Jonathan, I wish Edwin pulled out the certificate that you guys sent him, because he was one of the people who named it Chandra.
Proposed.
Oh,
Proposed
really?
it. Yeah.
Yeah.
When NASA had that naming contest.
Right. Yeah.
The
You
observatory.
know, Tyrell Johnson was one of the winners.
Yeah, and then
He was a high school student who later went on to become a gamma ray astronomer. So that was nice.
Oh, okay, yeah, and I think Rick Feinberg also got
Yes,
a
So
certificate.
he also picked it.
same as
Okay, yeah.
Edwin.
The runner-up was
we all
Curie, I
proposed,
think.
we all proposed the name Chandra.
Yeah,
but
well, it's
of
a
course
good name.
They picked the high
Thank you,
school
Edwin.
student.
It's a good
Yeah.
name. We appreciate it. We love it.
Thanks. Thank you.
Edwin,
Yeah.
Professor Chandra Sekar is with the University of Chicago.
Yeah.
So,
Yes. Yeah.
yeah. Thank you. So the next question here thank you for that very, very interesting information, Edwin. The next question from Dante De Jesus is, can charged particles traveling in a straight line, like train cars at relativistic speed, be able to produce X-ray when passing perpendicular through a strong magnetic field? So it's a physics question.
Yeah, I believe so. It's a little late in the Saturday evening here for me to be doing physics, but because of relativistic effects, even if they're at right angles, there is an aberration effect that causes some degree of interaction, and so you will get some X-rays.
Okay. Again, these are questions from our Philippine viewers. Again, Melanie Sitoy, how is a black hole formed, and how does Chandra detect it?
Right. So a black hole forms, well, there are a number of ways that they happen. The little black holes in our galaxy form when a very massive star explodes in a supernova, like some of the ones I've shown, and the center of the star collapses. The reason a star doesn't, like our sun, doesn't immediately turn into a black hole right now, its gravity is trying to crush it, but the heat in the middle from the nuclear fusion is pushing back. And when you burn up all the nuclear fuel and there's nothing left to push back, gravity wins. And in the right circumstances, if you have enough gravity, you can squish down and make a black hole. But the other way to make a black hole is these supermassive black holes in the middles of galaxies. And we're not sure yet how they form. We think they form just by gravity in the early universe. You start off with a very smooth universe. But this part of the universe maybe has 1 million atoms, and this part has 1,000,001. And so that extra atom means that this part has slightly more gravity, and it pulls on the left a bit more than the left pulls on the right, and so it steals another atom. And now it's got 1,000,002, and the other one's got 99999, right? And so it steals more and more, and so the universe curdles into lumps, and those lumps collapse under their own weight. And in the early years, there isn't anything to stop some of them. They get so overdense that they form black holes, and they become the cores of galaxies. How does Chandra detect the black hole? It doesn't detect the black hole itself. What it detects is the effects of the black hole on the gas around it. So if a star gets close to a black hole, the gravity of the black hole can tear it apart, and the matter of the star will spiral into the black hole. And as it's squeezed by the black hole's gravity, it gets very, very hot, 1,000,000-degree hot, and makes X-rays. And that lets Chandra see it. So that's what we're seeing.
Thank you. What is also amazing when listening to your lecture is actually with Chandra, we were able to see dark matter. That's really amazing.
Right. Well,
So
Chandra plus optical
yeah.
combined. Yes, exactly. No, that's a fantastic result.
Yeah. And this is a question then again from one of our Philippine viewers, Mr. Raymond Ang. How can amateur astronomers assist in Chandra observations, either prior to Chandra observing the target or as a follow-up to Chandra's observations?
Well, I think the most interesting way is what amateur astronomers already help us with monitoring of cataclysmic variable stars. When a CV, a dwarf nova, goes into outburst, often the amateurs are still the ones to notice this first. And then that might trigger a target of opportunity. Oh, this star is doing something interesting. Why don't we turn Chandra to look at it? And so I think that's sort of the main way is looking at things that are usually boring that have suddenly got interesting and we might not have noticed yet, alerting us to that fact. The amateur community has, particularly with work with the AAVSO, the American Association of Variable Star Observers, which despite its name, I think, has observers worldwide. And they're very good at coordinating that kind of data.
Thank you. Jonathan, do you have time for some more questions?
Sure, absolutely.
Yeah. So here's another question. In the X-ray image of the center of the Milky Way with Sagittarius A, there seems to be some spiral structure. Are the gases spiraling in to Sagittarius A?
Yeah, it's not actually spiral, but it's loops. And what's happening is there are very strong magnetic fields. And when you have very strong magnetic fields, you see the same thing, by the way, in high resolution images of the surface of the sun, that you get what are called flux ropes. You get there's an instability where if the gas collapses around the magnetic field and makes curved things, sort of like in the iron filings in a magnet in a high school physics experiment, right? You get these lines following the magnetic field lines. And that's what you're seeing in the center of the galaxy there.
And here's another question. Do planets emit X-rays and can Chandra observe them?
Right. Well, a small amount, right? And in particular, the planets themselves don't tend to emit X-rays, but if they have magnetospheres like the Earth, when the energetic particles hit the planet's atmosphere, that makes X-rays, and it's what in Earth we call an aurora, the northern lights, the aurora borealis, the aurora australis, right? And we can see that on Jupiter. So when we observe Jupiter with Chandra, we see two stripes, the north and south aurora on Jupiter. We don't see Jupiter itself, we just see the aurora. And so another thing that we see is comets. The comets themselves don't make the X-rays, but there's a strange process where the sunlight hitting the comet gas bounces off and gets converted up into X-rays. And so a thing called charge exchange. And so we can detect comets in X-rays as well. So planets aren't very bright in X-rays, and you know, exoplanets we don't really study, except what we study are we look at the host stars of exoplanets to see if they have a lot of X-ray flares. Because if you're looking for habitability, right, you might have this planet that's quote in the habitable zone, but if it's getting irradiated by enormous super X-ray flares every 2 weeks, probably it isn't a very nice place to live. So that's the sort of study we do that relates to planets.
Thank you. In relation to X-rays again, in case there's a super flare on the sun, do we need to worry about solar X-rays?
Worry about? I don't think the X-ray flux itself would be a threat to us. It would make a big aurora. I mean, I need to worry about it because it would damage Chandra. But it wouldn't damage you. You know, we are protected by our magnetosphere, and so I think we'd be okay. But it depends how big a super flare, right? How super a super flare. There's some level at which, yeah, it would be bad for us if sufficiently much X-rays were produced by the sun, and we really don't know. We really don't know how big, what the upper limit is to how bad the sun can get, right? So, you know, that's something which we'll have to hopefully not find out by experiment.
And here's again another question. Can gravity and magnetic field in a black hole combine their pull on objects and particles?
Yeah, you have to take both into account. And when we do, in fact, that is where we get the jets from in the Centaurus A galaxy, the two jets that were coming out. And so there's a guy called Roger Blanford who worked with my colleague Roman Znayak back in the 80s to do the incredibly horrible, nasty math of magnetohydrodynamics in a general relativity black hole geometry. And I've tried to do it. It's really messy. But they claim to show that they can explain how the particles near the black hole get caught up in the magnetic field and accelerated instead of go into the black hole. And it needs both the gravity of general relativity and advanced study of electromagnetism.
Thank you, Jonathan. Do we have time for a few more questions? Yeah. So here is another one. If Betelgeuse explodes in a supernova, how will it impact us here on Earth?
Right. Yeah, it's a good question. I mean, certainly, Betelgeuse is far enough away, I think, that although it would be spectacular in the night sky, it would be great for amateur astronomers. I don't think we'd be damaged by the shockwave or anything like that. I'm trying to remember how far away Betelgeuse is. It's not one of the closer stars. Yeah, it's 600 light years away. So you know the supernova flux is going to be pretty small here. I'm much more worried about a more nearby star going supernova, but it doesn't look like that's going to happen anytime soon. There's no good candidates for that.
Thank you. So I think it was in one of your slides regarding the Chandra's replacement. Are there any plans to launch another X-ray mission?
Yeah, so there are a number of X-ray missions. Japan actually launched a very exciting one called XRISM, XRISM, and that has a new camera that can see many more colors than in the X-rays than anything has done before. But its vision is very blurry. It doesn't have Chandra's sharp imaging. It just has very, very good spectra. And so what we really want is something that combines XRISM's camera with Chandra's mirrors to get both. And there are a number of plans in the works, but none of them have yet been funded. We're facing very big budget cuts at NASA at the moment. And so things don't look great in the near future, but someday we'll get our act together to have a replacement for Chandra. And there are a number of intermediate proposals that my colleagues are working on for like mid-sized missions that would at least get us some of the way on the science that we want to do.
Thank you, Jonathan. And I think this is the last question. In Chandra's 25 years of existence, what do you think is its greatest discovery? Chandra's greatest discovery.
You know, it's so hard because Chandra is like a Swiss Army knife telescope like Hubble is. You know, what's Hubble's greatest discovery, right? I mean, we use it for
your favorite discoveries.
Yeah, we use it for new things every day. And so there's just so many. It's more about the number of discoveries than any one being spectacular. Having said that, I think the one I showed of the dark matter is the one that, for me, for my money, is the most profound and the most important.
Is the gravitational wave, sorry, I cannot really know, but the gravitational wave, is that also part of the Chandra?
We can't detect gravitational waves themselves.
Yeah.
But what we can do is we can see, like I showed from the one of the images, we can see the X-rays from the object that just died to make the gravitational waves. So we make gravitational waves when two black holes or two neutron stars merge into one, and that creates a big ripple in space-time that LIGO finds. But then once that settles down, it settles down into an ordinary explosion that puts out a lot of X-rays, right? So, you know, a tiny little thing that's only the equivalent of, you know, 1 trillion nuclear bombs or something like that. Nothing as spectacular as a black hole merger, but it's still enough to make a lot of X-rays. And so we can do the follow-up. And so again, I want to go back to this theme, right, of it's not just one telescope that you need. You need all the telescopes, and they all look at the same thing and get a different kind of piece of information. And then the scientist puts those pieces of information together, triangulates to get the story of what's going on. And so Chandra is a very useful tool to the gravitational wave folks as an additional piece of information on the things that are making the gravitational waves.
Thank you, Jonathan. I think that's the last question. Let me share my slide again.
Jonathan,
Yeah.
so have you moved, did you move here to Burlington now, or are you still in Cambridge?
Well, me personally, I'm still in Cambridge. But the Mission Control Center, the OCC, the Operations Control Center that was at Draper Lab, after 20 years, Draper Lab said, when we gave you the upper floor for your mission control, you said you were going to be a 5-year mission. We want our floor back, please. And so we had about a year to scramble and find a new place for our mission control center. So now, and the best place we could find was in the Burlington Mall. And it's right across the street from the steakhouse. And so we have this very, very spiffy, fancy new control center. It's really nice, but it's kind of a schlep to get out to Burlington.
I should find it. Basically it's like a mile away from us.
Yeah,
we can give you a tour.
Okay.
Yeah.
Great. Thank you.
Yeah, but nag me about it, and we'll not in the next month, but down the road we'll set up a tour. Yeah, that in July I'll be showing the summer interns round, so you can come along then maybe.
Okay.
Oh yeah, that would be fantastic.
Yeah.
Okay.
No, it's great. So you know, we have this whole team, right? That it's really, for the other people who are listening, it's really very spacey. You know, that they are sending commands to the spacecraft, but first they have to talk to the dish operators in either California or Madrid or something like that. And so, you know, they have the full setup with the headsets, and they go, you know, Madrid, this is Cambridge, do you copy? And they check all of that, and then they get the signal down from the satellite. And the first thing they look at is they have this screens and screens of information reading down from the satellite that's basically asking the satellite, how are you feeling today, Chandra? And just occasionally Chandra's going, I'm not feeling good at all. And there's all these red lights go off, and everybody's beepers go off, and then we have to go. And we've had that a bit lately. Again, the eyesight of Chandra's star tracker isn't so good anymore, and so it can't find the guide star. And so it goes, help, help, I don't know where I am. It's like a little cat that gets scared and hides under the couch, and we have to coax it out again and get it going again. So there's a lot of work in an aging spacecraft just keeping it running. And our team is fantastic at it and really do a great job. But that's where, you know, you really feel like you're in a space program, that you're really dealing with these you know, direct communications with the spacecraft and with the Deep Space Network.
Burlington is a good choice, I have to say.
I'm not sure I agree, but
yeah, just the next town over is actually where they build the heat shield for the
Orion spacecraft.
yeah, the Orion spacecraft.
is that what used to be AVCO? Or...
Yes.
Yeah.
Okay. Are there any other questions from the panelists before we? Thank you so much, Jonathan, for your time.
It's been my pleasure. Thank you for inviting me.
Jonathan, if you don't mind, I just have a couple of questions.
Okay, go ahead.
The first one is, you deal a lot with X-rays, and they're very energetic. And even more energetic radiation would be gamma rays.
Yeah.
And is there anything beyond gamma rays that's even more energetic in terms of radiation?
Yeah, we don't have a really separate name for it, but basically everything everything from there on is gamma rays. But we distinguish nowadays between MEV gamma rays, GeV gamma rays, and TeV gamma rays. And so, Emmy, this is million, billion, and trillion electron volts, which is the currency of the energy of these things. And so the Fermi satellite is able to observe in MEV and GeV gamma rays. But the TeV gamma rays, and even beyond, the way we detect them is we actually have a little optical dish in Arizona with a photometer that works very, very fast, microseconds. And the enormous TeV gamma ray photon hits the upper atmosphere, creates a particle shower, like in an accelerator, which makes and the particles decay into gamma rays and photons that make a very brief, and optical photons ultimately, that make a very brief but bright flash in the sky. And we detect those bright flashes, and so we can detect when the gamma ray has hit the atmosphere. And it turns out, I remember when they were still looking for these things, and they'd been working for 10 years, and they only had upper limits. And then they saw the Crab Nebula finally. And then they saw Markarian 421. And now they have about 20 sources that are shining in this incredibly high energies. And they're almost all blazars. They're these jets from quasars that happen to be pointing right at us. And somehow they're accelerating particles to absolutely enormous energies such that they zip all the way across the universe and survive until they hit the Earth's atmosphere. And so that is still very cutting edge, the ability to detect them and measure them is much more limited than it is for X-rays. But people are pushing that energy frontier.
Okay. And the other question I have is, ever since Imelda and I have known you back in the mid-1990s at Sky Telescope, you've been chronicling all the satellite and rocket launches all over the world.
Yep, that's my other life.
Yes, and I know you're very passionate about this. So my question is, since you're so involved with, rocket launches and satellite launches and even spacecraft launches, what can you say about the SpaceX program to launching Starlink satellites?
Right, the mega constellations.
Yes.
So there's many thousand Starlink satellites now up, and there's other companies that want to launch similar large constellations. OneWeb has 600 satellites so far. The Chinese are talking about a 13,000 satellite constellation. I think it's problematic. We're getting to a point now where we're really affecting the environment in outer space in a number of ways. One way that's of interest to this audience, of course, is that when you take pictures of the night sky, you're going to have satellite trails on your pictures. And at the moment, it's at the annoying level. But when there are 10 times as many satellites as there are now, it's going to be really a problem to do some kinds of science in astronomy. We're not going to see with Starlink, they've made the satellites a bit fainter. We're not going to see them outnumber the visible stars for an amateur looking at the sky with their bare eyes. But other constellations may. So some of the constellations that have been proposed, but probably won't fly, would actually end up with more visible satellites than stars in the sky. And I think that would be a bad outcome. There are also concerns about collisions between satellites with that many satellites. And there are concerns when you retire the satellites and burn them up in the atmosphere, that we're actually now putting up, incinerating metal in the atmosphere at a rate that could actually change the atmospheric chemistry and cause climate problems, potentially. And so there's active research on that right now. And so it's just, whenever you up the level of human activity in some sphere by 2 orders of magnitude, which is what we're doing in low Earth orbit, you're going to have to revisit some of the earlier assumptions that you made that, oh, we don't have to worry about this or that. And so I think there needs to be, along with this massive industrialization of Earth orbit, there needs to be a lot of environmental impact study on really what is this going to mean.
And this doesn't include anti-satellite technology that's being developed by countries.
Right. That's a whole other issue is blowing up satellites and so
With
forth.
a million pieces.
And that's also obviously something we want to avoid. So yeah, so I think, you know, this has always been there's always been an issue with, you know, sustainable, environmentally responsible exploration of space. Comes up as well in things like planetary protection, sterilizing your Mars probes, and so on. But I think it's going to be more and more part of the discussion going forward as our environmental footprint on outer space becomes larger.
Great.
Yeah.
Thank you, Jonathan.
Thank you.
Any
Really
other?
appreciate what you're doing here, Jonathan. I'm pretty sure you have inspired a lot of people and opened the minds and the eyes of many. As I always say in talks that we give, you know, our knowledge of this universe is based on what our instruments can detect and what our minds can comprehend. You know?
That's right.
Okay, on that note, I would like to thank you again, Jonathan, for your time and of course for passionately sharing with us your experience with Chandra and the science behind it. And let me allow us to present with you our humble ALP certificate of appreciation for this talk. And I would like to read it. This certificate from the Astronomical League of the Philippines is presented to Jonathan C. McDowell, PhD, for his invaluable insights, experiences, and expertise shared with the participants of the online talk entitled Chandra and the Invisible Universe, given this 18th day of February 2024, signed by Mr. James Kevin T., President, and Dr. Jose Francisco Aguilar, yours truly, Vice President. And of course, before we let you go, can we have a group picture with you? Is that okay?
Sure.
Yeah.
Melda, Edwin, can you be a little tighter? Yeah, a little. Yeah, that's it. Okay. Okay, 1, 2, 3. One more. 1, 2. One more. 1, 2. Okay, got it.
By the way,
Thank you.
Jonathan,
Thank you,
Mr.
Jonathan, for
James
yeah.
Kevin T. is our president, the president of the Astronomical League of the Philippines.
Oh, great. Very
Thank
good.
you, Jonathan, for joining our
Yeah.
webinar. Yeah.
Thank you, Jonathan,
Thank you again for inviting
sharing
me.
your time with us tonight.
Yeah. Well, I wish everyone in the Philippines the very best.
And we hope you inspire the next generation of X-ray scientists, X-ray
Indeed.
astronomers.
Thank you. Thank you. And then I'll just make some announcements here. James, can you do some announcements regarding the activity for our opening of the National Astronomy Week for Astronomical League of the
Okay.
Philippines?
Yes, thank you, Jet. I'd like to announce that later we will have free telescope viewing at SM Mall of Asia, SM by the Bay, from 3:30 to 9 o'clock p.m. So the first part, around 3:30 to 5:30, we will be doing a free solar viewing. So there are some activities in the sun right now. So we'll be showing the sun in white light as well as in hydrogen alpha. Then onwards in the evening, we will try to point the telescope to the moon, Jupiter, as well as Orion Nebula, and Pleiades, and other bright, interesting stars that can be seen in the Manila. So this will be duplicated again on the 24th, on the Saturday. So that's it.
Thank you, James. And before we conclude today's webinar, I would like to thank all our attendees again for joining us. We will be sending your certificate of attendance by email to all registrants who were able to join us today. And this is actually the 23rd webinar in our ALP Astronomy Expert Speaker Series. Since we started almost 2 years ago, our first speaker was the late Dr. Jay Pasakov on April 23, 2022. Our other esteemed speakers since then were Mr. Salt Livey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, Mr. Dave Eicher, Professor Matthew Barlow, Mr. Scott Roberts, Father Christopher Corbali, Mr. David Levy, Mr. J. Kelly Beatty, of course, Imelda Johnson and Edwin Aguirre, Dr. Daniel Green, Dr. Heidi Hamill, Dr. Deborah Elma Green, Brother Robert Mackey, Brother Guy Consolmano, Hilary Andales, Dr. Valentin Pillay, and Mr. Wally Pocholka, Dr. Robert Nemiroff, Dr. Michael E. Brown, and for today, of course, Dr. Jonathan McDowell. And we are so grateful to all our webinar speakers who very generously gave their precious time to share their knowledge and expertise to the world amateur astronomical community. We can never thank you enough. And for all those who missed all our previous ALP Astronomer Expert Speaker Series, you can view the video recordings of our past webinars, including this webinar, at your convenience at our official ALP YouTube channel shown here. So just search Astronomical League of the Philippines in YouTube, and you can video all of these. You can watch all of these video recordings of the ALP Astronomy Expert Speaker Series. And for our next speakers, upcoming speakers, we will be having, hopefully, Dr. Meg Urey, a professor of physics and astronomy at Yale University, whose topic will be the supermassive black hole at the center of the Milky Way. And the next speaker will be Dr. Michael Kelly, who is a program scientist of the Planetary Defense Coordination Office of NASA headquarters and an astrophysicist at Yale University. He will be talking on the topic, Defending Earth from Asteroid Impacts. Please wait for further announcements regarding these upcoming online talks or free online talks at our ALP webpage, astroleaguefields.org, and of our ALP Facebook page. So thank you everyone for attending. Happy National Astronomy Week. Join us today and this afternoon for the ALP free telescope viewing, and clear skies always. For the panelists, I will be sending the Zoom link. We have a short 1-hour meeting after this. Thank you, everyone.
Okay.
Thank
Bye.
you.
Thank you.
Bye-bye.